In this lecture, we look at rotational kinetics or rotational motion. The description of rotational motion is nearly identical to the description of linear motion. We use quantities that are parallel to each other. For example, the position in linear motion was represented by a variable like x. For rotational motion, there will be an angular variable, theta, which will play the role of angular position. The displacement is delta x for linear and delta theta for angular for the rotational motion. Velocity was represented by a b in linear, and it'll be omega in angular, so there's an angular velocity also. There's an acceleration in both. The linear acceleration was often represented by an a, the rotational acceleration by the angular acceleration alpha. The motion of an object, or the linear motion of an object, depended greatly on its inertia, or the measure of that inertia being the mass. The angular rotation of an object will depend on another quantity called the moment of inertia I, and we'll see more about that later in another lecture. The basic relationships between these quantities are the same. For example, the velocity is just simply the change in x over change in time, whereas the angular velocity is the change in theta, or the change in angular position over the change in time. So the analysis will be the same. For example, let's look at a case of constant acceleration. If we look at the equations for the linear motion, we recall that the velocity is equal to the initial velocity plus the acceleration times time. For the angular or rotational motion, we have that omega, the angular velocity, will be equal to the initial angular velocity plus the angular acceleration alpha times time. And the position formulas are identical too. We have the same form. X is equal to the initial x plus the velocity times time plus 1/2 the acceleration times t squared. Theta is equal to the initial angle plus omega 0 times time, the initial angular velocity, plus 1/2 times the angular acceleration times time squared. So if in the linear case, we might look at a situation where at time equal to 0, a car is traveling at 20 meters per second, then accelerates at 5 meters per second squared for 10 seconds. How far does the car travel in this 10 seconds? Well, we're only asked how far it travels in the 10 seconds, so the initial position doesn't really matter, so we set that to 0. Then we have the velocity, which is 20 meters per second times the time, plus 1/2 times the acceleration, 5 meters per second squared times the time squared. And if you do the arithmetic, you find out that's 450 meters. If you look at the rotational or angular case, if at time equals 0, a wheel is spinning at 20 radians per second, and it then accelerates at 5 radians per second squared for 10 seconds, how far does the wheel turn in this 10 seconds? Well, theta is again equal to 0 radians because we're only concerned about how far it moves in that 10 seconds while it's accelerating. So we have the 20 radians per second times 10 seconds plus 1/2 times 5 radians per second squared times 10 seconds squared. And you do the arithmetic again, and the answer is 450 radians. Let's look at these angular quantities in more detail. The angular position, theta, is defined in terms of the picture shown below. We have a circle, shown by the dotted line, and a particle that's moving along the circle. The angular position of that particle on this dotted circle is measured with respect to the x-axis or the horizontal axis. So what is the angle between the horizontal axis and its current position is the angular position. This angle is positive if it's counterclockwise from the horizontal axis. So what's the position shown here has a positive theta. If it was below the axis or going clockwise, it would be negative. The distance along the path from the x-axis is equal to r times theta, the radius times the angular position. The angular velocity is equal to omega times the time derivative of the angular position, d theta dt. If we look at a particle that is moving around some fixed axis. In this case, the particle is going around in a clockwise fashion about the vertical axis shown. Then if it goes clockwise, the angular velocity is negative. If it goes counterclockwise, the angular velocity is positive. If we're interested in knowing what is the velocity along the path, or the tangential velocity of the particle at any particular point, it's given in terms of ds dt. That's the time derivative of the position along the path. And that's equal, the radius r is constant, so it's r times d theta dt, but d theta dt is the angular velocity, so the tangential velocity is equal to r times the angular velocity. There is no radial velocity because it's moving along a circular path. The angular acceleration alpha is equal to the time derivative of omega. And if we look at the tangential acceleration along the path, that's equal to the time derivative of the velocity tangentially along the path, so dv dt, and that's equal to the radius times d omega dt, or r times alpha. So what we see is all these linear quantities, that describe the linear motion of the particle along the path, are related to the angular quantities by multiplying by r. So we have s is equal to r theta, the v tangent is equal to r omega, the acceleration tangential is equal to r times alpha. Of course, you should remember also for a particle moving in a circle that there is another portion of the acceleration, and that's the centripetal or radial acceleration, which is given by the tangential velocity squared divided by r.